Hi, welcome to this tutorial series on graph basics. This video introduces the definition of paths in an algebra graph system and what a k-hop neighbor is. To understand the paths, we first need to understand hop. A hop in the graph is walking from one node to another via an edge. Hop describes how two nodes are connected, such as a course is offered by a department, a student studies in a department, or a student enrolls on a course. We can either hop along the direction of edge or hop against the edge. So there's no problem to hop and describe that a department offers a course, a department has a student in it, or a course has a student. Compare hops on the graph with the operations on relational tables. One hop is relative to joining one record to another among two or three tables. For example, walking from a department to one of its students is equivalent to joining the department table with the student table. Walking from a course to one of its students is equivalent to joining the course table with the enrollment table and the student table. Keep hopping on a graph, which is walking from node to node continuously without rewalking the same edge. The series of nodes and edges that have been walked form the paths. Here is an urban map, and this is Jason's house. Jason works in a pet shop. The black line shows the route he commutes every day. Record this route in both directions. There are paths that each has only one hop. Hop is the minimum unit of paths. Last week, Jason was on night shift, and he went to KTV before he went to work. This temporary route is a path that starts from Jason's house, arrives at the KTV, the traffic light, the clinic, and finally the pet shop. It is a 4-hop path with no road section retraveled. As a counterexample, if he traveled back to his house after the KTV before he went to work, it is not a legal path supported by algebra graph system. In an algebra graph system, the edges do not reoccur in a path. Last Sunday, Jason had a date with Alice. He met Alice at a pizza restaurant where they had lunch. Then they went to KTV and Jason sang the song he practiced the whole week. In the end, Jason sent Alice back home and went his home by himself. From the map we can see Jason's house and the traffic lights are retraveled in this Sunday journey, which create two circles. This long route is still a valid path by algebra's definition, in which case we call a path has circles. This example summarizes the concept of paths in the algebra graph system. Paths is a series of connected nodes and edges where nodes are allowed to reoccur, but edges are not. To tell the algebra graph system what paths we are looking for, we usually provide which node is the source of the path and which node is the destination, and how many hops the path consists of. For example, tell the algebra graph system that we concern about paths from node A to node C within 3 hops. The system will find 5 paths. Almost certainly, we won't be satisfied with this result, and we want the graph system to search more precisely. Imagine the paths being discussed are driving route, and the direction of edges represent the direction of traffic. As driving against the traffic is forbidden, any hop against the edge should be prevented. That means the brown path should be ruled out, because its first hop, the hop from A to B, is against the edge direction. So tell the algebra graph system that all the edges should be pointing to the right, which is along the direction of hop. Beside the direction of edge, limits can be set on nodes and edges to rule out the paths that we are not interested in. This is called setting filtering conditions in context of algebra graph system. For example, we may want to bypass the heavy traffic in some road sections. Save the traffic speed as an edge property. The algebra graph system will filter out the blocked road section based on the property value. Or we want to avoid the intersections with high accident rate. Save the accident rate as a node property and apply the filters. Last but not least, shortest path is another preference in many circumstances. Look at the blue and yellow paths in the map. No matter you choose the route with the least intersections or with shortest mileage, both choices are in the scope of shortest path. Consider the path from node A to node D regardless of number of hops. We can find 4 paths. The number of hops is the number of edges in the path. The total weight is the weight sum of each edge in the path. These numbers are the weight of edges. Then the total weight of each path can be calculated. There are 2 types of shortest paths. The unweighted shortest path is the path that has the least number of hops. The aforementioned route with least intersections is a scenario of unweighted shortest path. The weighted shortest path is the path with the minimum total weight. The route with the minimum mileage can be found by calculating the weighted shortest path when the weight of edge represents mileage between locations. The algorithms used to find shortest paths are BFS and Dijkstra, which will be introduced in a separate video. The next concept to introduce is k-hop neighbors. Here's a target plate that has 3 rings. The rings are named after their rankings of distance to the bullseye. Now let's draw a graph on the target plate. We first draw a node number 0 on the bullseye, then draw the rest of nodes on the rings. When drawing nodes on the ring's name equals the number of hops of unweighted shortest paths from the node number 0 to the node being drawn. For example, the unweighted shortest path from node 0 to node 6 has 2 hops. And that's why we put node 6 on the second ring. We call the node on the bullseye the subject node, and the nodes on the rings the neighbors, and we rename the rings as k-hop. K-hop index of a neighbor is the length of unweighted shortest path from the subject node to the neighbor. It tells the least number of hops to reach the neighbor from the subject node. The k-hop index changes only when the constraint on hop changes, which essentially leads to the change in the unweighted shortest path. For example, if we consider the direction of edge in the graph and restrict the edge in each hop to be right-pointing, which means we cannot hop against the edge. In this case, node number 2 should not stay on the one-hop ring anymore, since when hopping from node 0 to node 2 via the edge between them, it is going against the edge direction. The path should hop from node 0 to node 3, then to node 6, and finally to node 2. The k-hop index of node number 2 becomes 3, and it should be put on the third ring. Beside the direction of edge, many other constraints can be applied on hops, such as schema and property values of nodes and edges. When the constraint changes, the k-hop index of a neighbor should be reassessed. The last thing to remind: not all the neighbors will get a k-hop index, since some constraints just prevent the neighbors from being reached by the subject node. This is the summary of this lesson, and please follow our lessons in the future. We will show you more about algebra graph system and graph query.